Okay, you guys, welcome to your bonus molecular geometry lecture. If you are thinking about taking AP Chem next year, you should definitely watch and take notes. We certainly will do this again in AP, but it's one of those things where these structures start to get really complicated, and the more times you see them, the easier they are to work with. So let's go to 5 domains. So remember, we left off in the 4-domain tetrahedral family, right? So there's my 4 domains. Let's pretend they're all just bonded pairs. Ooh, ignore those lone pairs. Okay, so we're working with this 4-domain family. Can I tie a 5th balloon? Let's try. 5th balloon. Get away from the microphone so you guys don't have to listen to the sound quite as obnoxious as I have to. Aha. A 5th balloon on my structure. Now, how do I want to hold this so that you guys don't see any lone pairs? Do you guys now see how there's a top balloon and a bottom balloon? Do you guys see that right there? Okay, I've got a balloon on the top and a balloon on the bottom. And around the middle, I have 3 equidistant trigonal planar balloons. They don't look quite equidistant because my knot is all like on one side. There we go, that's a little better. Okay, ignore the lone pairs. All these balloons are the same size. So I'm going to introduce you guys some new vocabulary for this 5-domain family. And that is that this balloon on the top and this balloon on the bottom, these balloons are called my axial domains. Whereas these balloons here along the middle, around the middle of the molecule, these are my equatorial domains because they are going around the equator of the molecule. Okay, you guys see that? I'm not very visual, so I really need these balloons to help me. So hopefully they're helping you as well. So those top and bottom balloons are your axial domain, and the 3 around the center are equatorial. This shape molecule is called trigonal bipyramidal because you basically have 2 little pyramids. It might be easier to see on the molecule itself as opposed to with these balloons. Here's the molecule. Here are my top and my bottom axial domains, right? No, this way to center. Gosh, it's backwards for me. This way to straight, okay? And if I spin along my axis, you can see those 3 equatorial atoms at 120 degrees around it. So we've got 2 bond angles this time. There is a 90-degree bond angle between the axial and equatorial domains. So here you have a 90-degree angle. But then between your 3 equatorial domains, you have, or your 3 atoms in your equatorial domain, you have a 120-degree angle. And the word trigonal bipyramidal comes from this little pyramid that you have down on the bottom and this little pyramid you have on the top between your 3 equatorials and your top axial and your 3 equatorials and your bottom axial. So this is your standard trigonal bipyramidal 5 bonded domain molecule. Should we draw an example? Yes, we shall. Okay, let's think of a molecule that does this. Phosphorus pentachloride. So I hope we were working in green before. PCl5. 5 plus 7 times 5. 7 times 5 is 35, plus 5 is 40, divided by 2. Yikes. It's a lot of electrons, 20 pairs of electrons, and I did not leave myself enough room. I'm going to go like this. I'm going to go 40 divided by 2, 20 pairs. So I have more room for my Lewis structure. Oh, I need my good eraser. That's not working. There we go. All right. so now let's draw in all of those 20 pairs of electrons. So I've got my phosphorus. Now, you guys, I'm going to draw my axials in first. So I'm going to try to start making my Lewis structure look like my geometry. So there's my chlorine here and my chlorine there. And I'm going to draw my 3 equatorial chlorines like so. Just to make it easier to start making my Lewis structures match up better to what my geometry is going to be in the end. Okay, so I used up 5 pairs, so I've got 15 pairs remaining. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, a little squishy up here, 11, 12, 13, 14, 15. Beautiful. All right, so when we're talking about domains, how many domains do I have around this phosphorus? 1, 2, 3, 4, 5 domains. Oh, fiddle faddle. Wrong color. 5 domains, and all 5 of them are bonded. Now, to draw the geometry, I might use like, you know what I might do, you guys? I might do different colors for axial versus equatorial. Maybe that'll help you see it. Let's do my axial in blue. That'll be fun. Chlorine. Chlorine. And we'll do the equatorials in green. Chlorine. 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 There's 2 bond angles here. There is the 120 degree equatorial bond angle. And from the axial to the equatorial is a 90 degree axial to equatorial bond angle. Okay, now the name of this shape is trigonal bipyramidal. I'm always afraid on this right-hand side that I'm going off screen. I did not. Hooray. Sorry, I have to jump between screens to see what you're seeing. All right, now let's start getting crazy. I'm not going to draw a purple line, you guys, because I'm going to stay in this 5-domain family. But let's imagine that one of these bonded domains becomes a lone pair. And an example where that occurs is SF4. I'm just going to save the trouble of counting and drawing, or, counting all of these up. Just take my word for it, you guys. Now we're going to have a sulfur bonded to. There are my 2 axial fluorines. And my 3 equatorial is now just 2 equatorial fluorines. And had I counted up all of my electrons, you guys would believe me, don't you? In the interest of time, you'll believe me that when I get to this point here, that I'm left with 1 pair remaining, and that pair needs to go on my central atom. So I still have 5 domains. Okay, so let's look at our domains. 1, 2, 3, 4, 5. 5 domains. And so when you have 5 domains and 4 of them are bonded and 1 of them is lone, you have a new shape. Now, the lone pair is going to go on the equatorial plane. And the reason for that is if it's on the equatorial plane, it's got a 120 degree bond angle to work with. And that's the bigger of the bond angles. Remember, lone pairs repel more strongly. So it's more appropriate for us to draw that where there is more space, which would be on the equatorial plane. So if the lone pair is equatorial it minimizes the number of 90-degree repulsions that you would have to have. So you're going to put that lone pair equatorial. Now, what was I doing here? I was going to go central atom, sulfur, and I'm going to draw my axial domains in blue. There's one of my fluorines. There's another one of my fluorines. And now back to green for my two equatorial fluorines. And my lone pair is equatorial as well. So what ends up happening is these bond angles all get a little bit squished. The 120 goes to a little less than 120. The 90 goes to a little less than 90. So you get a less than 120-degree bond angle, and you get a little less than a 90-degree bond angle. The name of this shape is seesaw. Perhaps if I had drawn it differently, you guys would see the seesaw better. Like if I drew it like this. There are your 4 fluorines. There's your lone pair sitting on the top. Do you guys see the seesaw now? All right, good. I hope you all said yes. All right, so there's your 5-domain family with 4 bonded and 1 lone. Let's do another example. Sticking with the 5-domain family. Let's do ClF3. Chlorine trifluoride. You guys can probably see where we're going to go with this. We're going to go with 2 lone pairs this time. Okay, so we're going to go central chlorine. And we've got a fluorine on the top, fluorine on the bottom, and a fluorine on the side, and all of our lone pairs. And this time, when we get to the end, you can see where I'm going with this. We're going to have 2 lone pairs left over. So they're going to go equatorial as well. I just drew them. I just sort of went to the other side of the molecule so you could sort of see this better. It wouldn't have mattered where you did your lone pairs because remember, you're symmetrical around the center of that sulfur, right? That equatorial domain is symmetrical. So I just chose to draw my 2 lone pairs over here this time and my bonded pair over there. Doesn't matter. Okay, so you guys can still see if we're going to count up all of our domains this time. 1, 2, 3 bonded domains, 1, 2 lone pairs. So we're still in the 5-domain family with 3 bonded and 2 lone pairs. Again, those lone pairs are going to go equatorial. So I'm going to draw my central chlorine. And maybe I'll just go all equatorial while I'm in green here. There's my fluorine. There's my equatorial lone pair. My equatorial lone pair. And here are my axial fluorines. Here, this molecule is called T-shaped. You guys see the T between the fluorines? T-shaped. Ooh, and I didn't go too far either. Excellent. Okay. Oh, so we need a bond angle here. The bond angle here, now there's no more 120-degree bond angle anymore, you guys, because a bond angle is the angle between the bonded atoms. And the only bonded atoms on the equatorial plane is this one fluorine. So you don't have a bond angle, let's say, between this fluorine and that lone pair. So really the only bond angle we're concerned with is the axial bond angle, the angle between the fluorine and the fluorine, the axial fluorine to the equatorial. Or you could even talk about the bond angle between this fluorine that's axial to the bottom fluorine that's axial. And of course, this is going to be a little bit less than 90 degrees because of these repulsions. Now, because these repulsions are in a different plane, they're not going to be so significant. So a lot of the times you'll see here in the seesaw and here in the T-shape, you'll see these bond angles reported as 90 degrees because the equatorial to axial repulsion isn't quite as significant as had it been if they were all in the same plane. So this is our T-shaped with our generally 90-degree angle. All right, let's go to 3 bonded and 3 lone. Xenon difluoride. And this is the last of our 5-domain family. If you see my pattern here, you guys, you'll notice that we're gonna go to, oh, I'm sorry. Did I say 3 and 3? That would have been 6-domain families. I meant to say reversed, 2 bonded and 3 lone pairs. So here in this molecule, we're gonna end up with 2 bonded atoms. The 2 fluorines, all of them with their lone pair electrons. And you're going to be left with 3 pairs of electrons, and they're all going to go equatorial. If all of these are taking up that equatorial plane, we're back to just the axial domain. So here we have 5 bonded, 5 total domains. Can you tell I'm getting tired, you guys? I should have done these 2 lectures on 2 different days. 1, 2, 3, 4, 5. 5 domains. Now we're talking about 2 bonded and 3 lone pairs. So when this happens, when all 3 of these lone pairs are now on that equatorial plane, it's going to push those axials straight into a 180-degree bond angle. So they're just going to be straight up and down or straight side to side, however you feel like drawing it. There's your xenon. And here are your axial fluorines. And these lone pairs, which we could draw in if we want, there's not going to be a bond angle at all there anymore. I know that doesn't look super 3-dimensional. Maybe I'll pull my balloons back out for you guys to get a better look at this. So here, my bond angle for my axial domain is 180 degrees, top and bottom. Those 3 lone pairs are just going to take up that total middle space exactly and push these guys straight up away from one another. 180 degrees is as far away as they can get. Now, when something is 180 degrees away from one another, 3 atom linear. So I will pull out my, oops, I just made a random line. Let's pull out the balloons. So now imagine with our balloons here that all of the balloons around that center, so there's 1, 2, oh, I think I need my marker. 3, all 3 of those guys are no longer bonds, right? So all along this center, there's a lone pair, oh gosh, and another lone pair. You guys can't see this very well. Get where I want you to be. Okay, lone pair, lone pair, lone pair. Turn your face. There. So all that's left is this top-bottom axial domain. 180 degrees apart. All right. Oh, you guys, it's time for me to tie on a 6th balloon. This is going to be interesting. This is where I usually pop one. But let's see if I can manage it. Probably should have taken my rings off. I did it. I did it, you guys. I wish I hadn't drawn all those lone pairs on everywhere. Do you guys see what has happened? Do you see how no matter which way I turn this, everybody's 90 degrees apart from one another? It's like a big symmetrical bubble. Ignore the lone pairs. This, where we have 4 guys along our equatorial domain. See those 4? So if there's 4 along the equator, that's all going to be 90 degrees away from each other. And of course, top to bottom are 180 degrees away from each other, but 90 degrees away from the equatorial. So our axial is 90 degrees away from our equatorial. And the equatorial are all 90 degrees away from each other. So this is a symmetrical octahedral geometry. Looks like this. So here's my axial, and there's my 4. Why can't I get this straight? There's my 4 along the equator. No, I need to go this way to get to the middle. Okay. Now, it doesn't matter. Could I turn it like this and make this my axial domain? There we go. Yeah, I could, right? Doesn't matter which way you turn it. It's a symmetrical molecule. 90 degrees everywhere. When you have 6 things bonded to your central atom. And the octahedral is 8-sided. So you've got like a little 1, 2, 3, 4-sided pyramid on the top and a 4-sided pyramid on the bottom, like a diamond. And so this is an octahedral geometry. Let's draw a purple line between our 5-domain and our 6-domain families and do a few more examples. Here we go. All right, I need to draw a dividing line here because now we're going to 6 domains. Okay, here we go. SF6. I think this was our expanded octet example that we did when we were drawing Lewis dot diagrams. So let's just go straight to it. 6 fluorines, all filled in with lone pairs. Who can draw it first? Did you beat me? That was hard for me. I'm very uncomfortable with long silences, as you might have noticed. Let's count up our domains. 1, 2, 3, 4, 5, 6. 6-domain family. This time, all 6 of them are bonded. And so, let's draw our central sulfur with our 4 90-degree equatorial guys. I'm getting lazy with these circles, and those aren't going to be big enough for me to smush little fluorines into. Fluorine, 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 and my axial fluorines. 1, 2. Now, it doesn't matter whether you're talking axial or equatorial here, you guys. This is a symmetrical molecule. So our bond angle is 90 degrees everywhere. And this shape is called octahedral. Okay. Let's stay in the 6-domain family, but let's turn one of them into a lone pair. Bromine pentafluoride. And again, you're just going to take my word for it, you guys, that by the time we get to those 5 fluorines all bonded, we're going to have a lone pair left over to go on the central atom. Imagine how long this lecture would be if you had to wait for me to do all that mental math. You should always do out all that mental math, right? Because when you're doing a new molecule, you have no idea how many pairs you're going to have. So you have no idea what the geometry is going to be. But since I know what geometry I'm getting after, I'm picking molecules that I know will land me there. There's my lone pair left over on the central atom. Let's count up my domains. 1, if I'm going too fast, pause. 2, 3, 4, 5, 6 domains. Oops, wasn't I drawing like bigger lone pairs around my lone pair domains? Oop, there we go. It doesn't matter where you do that lone pair, you guys. This is a symmetrical molecule. I just gave you that axial one like for reference, but the lone pair could go anywhere because it's 90 degrees everywhere. So it doesn't matter where that lone pair goes. So that lone pair in my drawing is on the top. Big whoop. What matters is that we have 6 domains total, 5 that are bonded, and 1 lone pair. That lone pair is going to smush my 90-degree bond angle everywhere. So all of these guys are going to get kind of smushed downwards into this ugly little like spider shape. There are my 5 fluorines. They all got a little smushed to less than 90 degrees by that lone pair that I drew on the top. This shape is called square pyramidal. The reason why it's called square pyramidal is because we essentially squished that arrangement. You can sort of see the square along the equator. We squished that square downwards into a pyramidal shape. Do you want to see what that would look like with the balloons? I know you enjoy watching me struggle. So, back to my, uh-oh, now I can't even like fit it between my desk and my wall. All right, so let's imagine, give me a lone pair on top. All right, this lone pair on the top gets blown up bigger. If he gets blown up bigger, all of these guys down here get smushed, they get smushed down. Smushed, and this guy pops up taller. And that smushed 5 guys down at the bottom, 1, 2, 3, 4, 5, is a square pyramid because they got pushed down. Oh, look, my hand would have been a better option. Or I could go back to my molecule and imagine that instead of this being a bonded pair, a lone pair up here, I'm going to squish all these bonds downwards. And my 90-degree angle is going to get a little messed up down into a square pyramid because of the lone pair up here. All right. Do you have one more in you? One more example? Oh, you know, I have some lone pairs. So here's my square pyramid. Okay. One more. Here we go. All right. Last one, you guys. You're doing great. Xenon tetrafluoride. Are any of you stressed that I'm like using a noble gas? These heavier noble gases actually can be forced to bond. All right. Xenon tetrafluoride. All right. They don't always have to be fluorines. These halogens could be fluorines, chlorines, anything with 7 valence electrons that needs to bond out there. Okay, so I know I used a lot of fluorine examples today. We're going to be going to 2 lone pairs. 4 bonded, 2 lone. Xenon. Here are my 4 bonded. Fluorine. 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 Okay, here comes my uncomfortable silence. I'll be left with 2 lone pairs. And they're going to arrange themselves top to bottom, as far away from each other as possible. Let's count up our domains. 1, 2, 3, 4 bonded, 2 lone, top to bottom. So that we end up with nice 90-degree angles everywhere. They kind of pop them all back into place. 6 domains, 4 bonded, 2 lone pairs. So my xenon is central. And my 4 fluorines are equatorial. And my lone pairs are going to go axial, top to bottom. I'm going to push all these guys right back into the same plane and a 90-degree angle. Because they're all in the same plane, instead of being square pyramidal, they're going to be square planar. And I will end with one last look at the balloons. So, remember, we had this guy up top, taking up more space, smushing everybody down. Well, what if there was one on the bottom too? See that guy on the bottom? So big lone pair on the top. Oh, come on. This way. Big lone pair on the top, big lone pair on the bottom. That's going to push all these guys right back into the equatorial domain, 90 degrees apart from one another. What would that look like in a molecule? So here was my square pyramidal. Remember, it was kind of smushing these guys downward away from that lone pair. But what if I had another lone pair on the bottom, repelling just as strongly as this lone pair here on the top? Now all 4 guys are back in the same plane. Or if you wanted to think about it this way, all in the same plane. If you want to take those lone pairs away to really see how flat this molecule is, square planar. You guys, you did it. You went through 5 and 6 domains. Great job. What's next? Some polarity. We're going to look next at how the sharing of the electrons between these bonds result in polar bonds or nonpolar bonds. And that's going to depend on electronegativity values. And then we're going to look at how the polarity of the bonds in concert with the shape of the molecule determine if this whole thing is polar or nonpolar. And that's going to determine how it behaves and what kinds of properties that it has. So great job. That was a lot. And I'll see you guys at our next lecture.